a simple? Yeah, but it's a simple thing that you made. So I think that's pretty cool. So we will look at this later today as well, or at the start of the afternoon session. Just if you have something you think is cool, just send it to me. I'm very happy to look at everything you guys did. Okay, so today I'm going to talk a bit more. Based on trying to minimize the difference between neighboring points, and then finally we also discussed how we could do this by a tree, by approximating things which are far away, and by doing some sort of Taylor expansion. So today we're putting this on one side, we're going to ignore all of this, and we're just talking about fluids and what we call hydrodynamics here. So hydro would be the water. We're not talking about water at all, but we're going to talk about how we can simulate an ideal gas, which would be what we usually assume is the gas around in the whole universe. And so what are the methods and what do we need to do to get that to work? Okay, so to solve the equation of fluids, there are three main categories of methods that people use. And some might sound a bit similar to what we had yesterday in terms of the decomposition. So there are things which are based in the grid or on a mesh. And you can think of yesterday we talked about this particle mesh method where you use the grids to calculate all the forces. There are some methods that are based on particles. And again, you think of your yesterday, you have some tiny particles, this the Dirac distribution type idea to represent the fluid. And then there are some methods that are a bit more recent in between, where instead of having a mesh that doesn't change, we're going to have a mesh that will deform when the fluid is moving. And that's trying to get sort of the best of both of these options. Now, one way to think about it is like this picture, is to say there are essentially two ways you can try to simulate the fluid. One is if you follow what Mr. Lagrange was doing, or if you prefer Mr. Euler's solution. So the two ways you can think about it is if you have a river floating in front of you, you can either be looking at the river and then solving the equation from the side of the river, right? And then you have to take into account the whole motion of the water. Right? So if you're thinking about, I'm going to have a grid over my region of my simulation, I have the water or the gas going through my grid. Right? The other option is, if you prefer swimming, you can jump in the river. Right? And then what you do then is that you don't have to simulate the fact that the river is moving because you are moving with it. What you're then doing is only simulating or calculating the changes around you. Yeah? So this would be a lot easier. For instance, if you have a river that's really moving very quickly, that can be a lot easier because you already you can cancel all of that motion by being in the river. Maybe don't go in the river if it's moving very fast. But that can simplify things. So for instance, if you think about if you look at how everything is moving in the galaxy disk can be moving very fast. So it can be advantages to use this approach at the top because then you're already moving with the galaxy and you're only solving for the difference in motion. Okay, so the calculation might be, you don't have to take into account all of the bulk motion of everything. So the bottom ones, this would be something like a grid-based method where you have a fixed grid and the fluid is moving through the grid. And this one at the top would be more like a particle-based method, where you have particles, and the particles move as they did yesterday with the gravity. Right? Particles move, but then you are moving with the particles, and then solving the equations in that frame of reference. Okay, so what is it that we want to solve? So fundamentally, we have already seen this equation, I think, on Monday. So we have a continuity equation. The first one just says I want mass to be conserved. So the change of the density over time is related to the motion, the rho times u of the fluid here. this combination of derivatives of my internal energy. Right? So I get a du by d rho at fixed entropy and a d rho by dr. All right. Those two terms are relatively easy, right? So mv, that's mv. D rho by dr, that's also quite easy because I have my positions, define my density in terms of the position of the particle. That's rho is m times w, and that depends on the position of the particle. So I know how I can take this derivative. It's going to be some sort of combination of derivative of w. Okay, so this second part here, this is not too difficult. So we're only left with a question about what that thing here is. What is the change in thermal energy depending on the density? And that's where we eventually do some gas physics. So we can apply the law of thermodynamics. So what I want to simulate here is an ideal gas. If I had something else, I could probably change that to be another type of fluid. But what we're going to do is that if we look at, for an ideal gas equation of state, then the change of internal energy with respect to the density, so du by d rho at fixed entropy, is p over rho squared. Okay, so that's a choice. And this is now that we introduce something in the system to say this is gas physics we're doing and not just a very general system. Yes?
P is pressure.
Pressure, yes, sorry. P is pressure. Okay. So if I put everything together, so it's a big jump suddenly, but this is just putting together the two equations we had. This one we had before, that's what our first definition of the density. Okay. And this one is just coming out of the Lagrangian. Just putting this together using the Lagrange equation to tell me how I combine my equation for. So I have my d rho by dr by du, and so on. So I go through all of the math. I end up with this equation. The only thing you will not have is these omegas. We're going to talk about them in a second. But we have this p over rho square, which is coming from this equation of state business. And no surprise that because we're talking about derivative of rho, we should actually get derivative of the w. And so these equations here tell me, so I have to calculate, if once I calculate the density, I can calculate how the velocity and then the temperature of my fluid changes. And now the nice thing is, because we've done this through Lagrangian, which has specific symmetries, right? If you think about the Noether theorem and so on, every time you have a symmetry in your Lagrangian, you are conserving specific quantities. So our Lagrangian, for instance, is symmetric. Again, it doesn't depend on position in space. So I conserve momentum. I also conserve angular momentum. I conserve energy, and I conserve entropy. That means that I have a system where everything will behave nicely. I'm not going to be destroying, creating energy or anything, right? So if I'm just evolving this equation properly, everything should be going well. Okay, so this is just derivative. Now, so far we're like, well, what does it even mean? So we have a set of equations that conserve these things. We constructed Lagrangian, we don't really know where it comes from, and we sort of made only a sort of fluidy thing we have done is assume some sort of equation of state somewhere. It's unclear where this actually is. And the one small thing is the previous equation had some omegas. I don't want to go into these details, but basically they take into account, these are there. If you do the full derivation, they are there to take into account the fact that H itself can change. So you have additional derivatives that have been hiding a bit, that are necessary, but it's all the same thing. You're just doing conservation, it's just that then it's bigger than a screen, and it doesn't really change the spirit of the argument. But I just put them in the slides here. Any questions so far? Yes?
Why is this approach still smooth particles?
Oh, so it's of course because we use this smoothing kernel to calculate the density at the start. And so we have a set of discrete points, and we smooth over these discrete points with sort of a function to get values of the field everywhere. Yes? Okay, so the question now is, great, what have we actually done? We've written down a Lagrangian, got some equations. Why should I even have anything to do with reality? Just inventing physics terms here. Okay, so we have a set of equations. Good. What do they actually represent? We have not made really any obvious connection to gas and fluids. The only thing we have done is we assume the equation of state relating the density and the temperature. That's all we have done. So maybe it sounds like it's going to be fluid, but it's, it would be good if you look at the equation, you can say, oh, I can see this is clearly the earlier equations. At this stage, it looks like it's a combination of W and P and some weird things. So let's go back, and actually that's sort of answering part of the question, what do we mean about smooth particle hydrodynamics? Let's try to have another interpretation of this curve. So we constructed these W's to say, let's compute the number of people in the room or something. But I can think of it a very different way. So the first thing I can, if I go back, I can take any function, just like, let's go back, let's ignore the fluid dynamics for a bit. I'm just going to define a function A, which depends on position. And one thing I can always do is I can construct some sort of integral like that, where A at the position R is A at the position A prime, and I multiply by the Dirac delta. So that's again this function which is 0 everywhere, and has the nice property that it integrates to 1 and then integrates to the polynomials. Okay. So far, I've not done anything clever. This is always true, just sort of really finding something. What I can do now is to say, okay, that's a bit boring, but what if I now make my delta slightly wider? And slightly wider means I'm going to, see where this is going, introduce my W again. Right? So now it will have, not just being perfect, we will not just have the value at exactly R prime, we'll have also over a narrow range of space. Okay? So that's the Dirac delta. So if I do exactly that, so if I replace my delta by a W, and I can tail or expand because just to see what the level of precision of this is, I can say that A is still my value, is going to be the value of A at different points, multiplied by my kernel over given size. And then you could also look at all of the higher order terms if you wanted, but that's just the risk, right? So what we're doing here, we are saying I can get, if I know this value of A at specific particle points, I can construct A anywhere I want by taking sort of a smooth integral over these points. Again, I have to carefully choose W, but we already made some arguments before about what W should be like, especially if it's a Gaussian, that we discussed before would be a good idea, apart from the fact that it goes to infinity, it was a good shape. If I make my Gaussian go to, if I make the spread, the sigma of the Gaussian curve go to 0, then H, that makes H smaller and smaller and smaller, so that's going to make my value converge. And we know that if I take the limit of Gaussians getting narrower and narrower and narrower, they actually are a Dirac delta. Right? So that's the correct limit. That's the limit we actually want to achieve. Now for fun, I can do some extra things. I can divide by rho and multiply by rho. I haven't done anything useful. It's just because it's going to be useful for what comes next. So that's just exactly the same expression. And I can define, and I'm just using here the sort of angle brackets to say this is sort of the smooth approximation of A. So I can say the smooth approximation of A at the point R, I can calculate it like this, using this integral. That is still exact. Well, okay, not exact because I've removed all of the H square, H cubed terms and so on, but that's almost still exact. But what I can do next is say, okay, if W doesn't go everywhere to infinity, and I only have a certain number of particles, then this integral here will be pretty much 0 everywhere, apart from where I have a particle which contains information. So that, I can replace my integral by a sum, right? And how do I do these replacements? Well, rho times dr, so that's the density times the tiny volume. That's going to be the mass of my particle. So I get an m here. A of r prime, that's only defining the position of my particle. So it's going to be the value of A carried by the particle B. This is going to be the density and the position of the particle. Again, that's the only place where we define it. So that gives me a rho B. And then I still have my kernel. So I can define any quantity wherever I want. So if my particles have a quantity A, say pressure, an internal energy, an amount of magnetic field, an amount of dust, or whatever, I can calculate what A is anywhere in space, in between the particles, or on top of particles, or wherever, by using this smoothing operation. And so I smooth over my figures to get a good approximation of the value. Okay, so that's just thinking about this interpretation of the kernel. Just to give something, if what I can do here, if I replace, just for fun, if I replace A, if I say A should be the density, then these two densities drop out, and we go back to the definition we had at the start, that rho is defined by saying the sum, the mass of the set times the. Okay? So it's self-consistent. Okay, so if I now only have I, so why this works, going from the integral to the sum, is because I know the value of A only at the position of the particles. And so that goes back to the smoothing idea. I know now how to compute A everywhere, not just at the position of particles, although that's not necessarily useful, but we know how to calculate any field we want everywhere. So it's very continuous. I just have to use the correct number. But we can do better than that. What about the gradient of a function? Remember, if you go back to thinking about the fluid dynamics equation, what did we have? We had something like grad of, we had some like diff u, and then some grad, something, grad rho, and other terms that we have to compute, right? If you go back to really start of the fluid dynamics. So we should maybe think about, can we say something, so we know how to compute A everywhere, can we calculate grad A everywhere, or derivative of A everywhere? And so that's, we can apply the same trick. So grad A, I'm applying the same rule. So grad, another any rule so far. So A, we know this is our expression from A of the previous page. And if I want to take the gradient, I just have to put a derivative in front. But what I can do now is once I replace this by a sum, then the only thing, so this and this, again, this is going to be a number. This is not a function anymore. This is only defining the position of the particle. Same for the density, the mass as well. So the only thing that I can take the derivative of, and essentially it's just saying, can I move this derivative inside the integral? Then the only thing I'm left with is that I actually, instead of getting the W here, I get the gradient of W. Okay, so if I know A everywhere, each particle carries, say, pressure, and I want to calculate the gradient of pressure, all I have to do is sum over my neighbors, calculate M times the pressure divided by rho, and then I multiply by the gradient of my function W. So that's a very powerful way of now taking derivatives, but just summing over my neighbors. Okay? And I'm doing this here for the gradients, but by the same logic, and for the same set of operations, I can do this for all of the other usual operators. So I can calculate A, that we've done. I could calculate divergence of A, and then magically, if you do the whole thing, you end up with that times divergence of the W. I can take a curl or a rotational, and I can take any matrix operation operator of any order that I want. Okay? So this sort of smoothing operation that tells us how we can construct any field value. Just if you know the value of the particle positions, I can calculate the value of the field everywhere. Also, any of the derivatives, any of the usual combination of things like diff, curl, and so on. Good. So now we have sort of this translation rule. So we can, if I now have a set of equations like the one I had from my Lagrangian before, maybe I can look at these and say, ooh, I have something that looks like A cross grad W, and I can think in my head, oh, but that's if I have A cross grad W, I should translate it as being A cross derivative W. That's actually curl of A. Okay, so what I can do is I can show you the equation of the Lagrangian before, and we're going to move backwards. Every time we see one of these guys appear, we're going to translate it back into what it would correspond to in like the non-approximate version. So let's do that. So we have these equations. So this one we don't really have. We already have an interpretation to start with. But here I have something like grad W. Here, right? And here I also have a graph W. So I have P over, ignore the omega, so I have P over rho squared times graph W. So if I use my translation rules, what is this? That should be something like, that should be gradient of P over rho squared. I've dropped a few terms just to simplify it, but the same thing because otherwise it doesn't fit. So what I get something like that, which tells me this is minus grad P over rho, which is what I wanted. And then if I looked at the other equation, the one for the thermal energy, what I have is I have V dot derivative of W. So that should be a div by my translation rules. And indeed, if I do my replacement, I end up with minus Q over rho div V. Okay. Now what I can do is I can go to Wikipedia and find that's the Euler equation in convective form. So they're in Spanish at the same time. And that's what they should look like. Right? So d energy by dt, okay, it's just different notation here, minus d over rho right here. And d energy by dt, sorry, the velocity by dt minus square q. And because here you also have gravity included, which I've ignored today, but that's deviation. Okay, so we did this whole Lagrangian business. It wasn't obvious where that was going, but it turns out that the equations we have constructed, they correspond to a particle approximation of the Euler equations. That's what we want, because we wanted to do fluid dynamics. But because we constructed it from a Lagrangian, we also have all of these nice properties that matter, so that energy is conserved, momentum is conserved, all of this by construction. So that's a nice bonus that we get by having gone this way rather than thinking about it in a different way. So what is the algorithm now? How do we make a simulation? So we're going to start, again, we always need initial conditions. So I have a starting point where I have particles with, say, fixed mass and some internal energy U. So that will tell me at every point in space what is the temperature at that point. Or you can relate U and temperature is pretty much the same thing. Second step, I'm going to choose an H for every particle. And we have this set of two equations that have to be solved iteratively, but that's essentially you can think of saying, I need to find H such that I have about 50 neighbors within a sphere around me. Once I have chosen H, I can compute the density, because this sum over the neighbors of M times W. Once I have the density of every particle, I can apply the equation from the Lagrangian from before, so that would be like P over rho squared times rho W, and then the other ones for the internal energy. And that will give me the acceleration, so the dv by dt, and the du by dt, the change of internal energy of every particle in my system. So if I do this sum, that each particle loops over 50 neighbors, that gives this term, then I get my acceleration and my change in temperature. Now that I have an acceleration, I can change the velocity of the particle. If I have a velocity of the particle, I can move them forward to a new position. Somehow I have chosen a small time step size for some reason that it's small enough that it's going to work. So the particles move to a new position. And we can go back to here. Now we have to find a new H because everybody has moved. So it's not clear that the H, that the 50 neighbors I had before are the same. Maybe I need to look closer or further away. So you have to iterate again to find the correct value. Yes?
Why in any of the equations we don't consider the density of the point?
So I'm going to come to this. Yeah. So first reason is that we're doing the earlier equations that have no viscosity. But that's a problem. It's not how, because real fluids don't behave like that. But so far that's what we wanted. We said this is a set of equations we want to discretize, and that's what we achieved. So just visually, step one, all of the particles. If I'm interested in just the big particle in the middle, just a bunch of particles, try to find what is the correct radius that have all of my neighbors, so I can solve the two equations at the same time, sort of this and either bisection, whatever, just find the correct size of the neighborhood. Each of these neighbors, say here I'm choosing 30 neighbors, they're all going to contribute something to the density. Right? The particles which are far away contribute less because remember W is decaying, so these particles here has a small light contribution. These guys here have a darker, stronger contribution to the density. Then I know the density of that particle. Of course, I do this for all of the other ones as well. So now I know the density around each particle in my system. Step 4, I calculate this equation here. So again, it's E over rho squared times gradient of W, which we argue is the correct formulation of the acceleration. I'm not sure you do the other one for the internal energy at the same time. So all of these particles now contribute, right? For each, you can think of this as being, for each particle I, it's a sum here, but you can think of it if you were to program it, this would be a loop, like a for loop over the neighbors. So each of these other particles here is contributing a small amount of force on that particle. And then if I do the sum of all of these vector forces, that tells me where that particle should move. So I get the total acceleration. Step 5, now I have my sum. I'm going to move that particle whatever direction I should, given by the equations. And step 6, everybody has moved. I have to go back to the beginning and do the next step. So that's how you would essentially write an SPH code. The equations are relatively simple. It's mostly about finding the neighbors. So if you want to write a code that is very fast, the math operations is not very much, but you have to find a good way of finding all of the neighbors. Because for each particle, you have to look for every other particle in the system and ask, are you my neighbor? Then you have n particles looking for n neighbors. That's going to be n squared again. So you need a more efficient way. You need to be a bit more clever about how you can find neighbors fast. Otherwise, it's going to be much too slow. And you asked over there whether we could use what was related to the tree that we discussed yesterday. So if you have a tree in your code because you're doing gravity, then you can use that tree because the tree will tell you sort of what are its possible neighbors around. If they are probably in the same cell as you or one of the neighboring cells or something. So you can sort of reuse the infrastructure that was constructed for the gravity to use it for neighbor finding. That is much faster. Right? So that's the core of the algorithm. Any questions? No? But if you only have a few thousand or tens of thousands of particles, writing a loop in Python that loops over every particle and then loops over every other possible neighbor and just check the distance, it will work very well. It's very fast. It's only if you learn really big calculations to be more clever about it. For you. Viscosity and some final information. Okay, so one big problem, and I think the problem you identified already, is that scheme is too perfect. So we conserve momentum, we conserve angular momentum, we conserve energy, we conserve entropy. Is that what we want? Somehow, because we derived it, so there must be reason. But is that really what we want? Is that how fluids actually behave? And I think the answer you expect from that, from me, is that the answer is no. That's not what we want. We need to do something more. In particular, this kind of things can happen. It's just an extreme example of a shock. So you have something very fast. Here you have just a plane crossing the sound barrier, for instance. And that's creating a very instantaneous change in entropy, which we call shock. And that's at that point, we're not conserving entropy anymore. There's an increase in entropy that's instantaneous, or almost instantaneous. And that's the property of the fluids that we are missing here because we are exactly conserving entropy. So we cannot do a shock. We could not do that part of the calculation correctly. So if you have you can take two blobs of gas, right? And I can throw them at each other. When they arrive against each other, we expect the temperature to increase. There should be a jump in pressure, and something will happen. Right? There should be a shock, a jump in pressure, and some viscosity should be applied, and something will happen. Right? That is not part of the equations we have derived so far. We have derived something where entropy is perfectly conserved. We're never heating anything up, and that is not good because that is not how real fluids behave. So in this case, the plane would just go through. There would be no Mach prop. There would be, well, it would be able to go above the speed of sound, but it would just not create sort of a Mach cone or any shocks or anything. Also, you couldn't fly. If you don't have viscosity, planes won't fly. Okay, so what we need to do is that we actually need to add extra terms to the equations. We need to say fluids in reality are viscous. Maybe air doesn't feel like it has a high viscosity. Gas, like it's not like petrol or honey or water, but there is still a certain level of viscosity, and that is part of how fluids behave. Otherwise, we don't get all these shocks. And so what we need to do is typically people add this term. So they add to the acceleration something that will convert a bit of the, so if you have a shock, again, two blobs coming at each other, some of the kinetic energy will have to be transformed into thermal energy through viscosity. And so we need to add something to the acceleration here, and that will convert kinetic energy into thermal energy by it. And that will create some entropy dissipation, which will not conserve entropy. And that is exactly the goal, because that's exactly what happens in the shock. I don't want to go too much into the details of how this is constructed. The only thing is that this, you can think that this comes out of nowhere. Not quite. These terms that enter the equation, if you have ever looked at the Navier-Stokes equation, which would be the system of equations that actually describe the fluid more properly, because then it also contains all the normal viscosity terms. These equations here, so there's here contains, for example, an alpha term, and the sound speed and h. This can be related to the exact Navier-Stokes terms that we should actually be solving. So there is a bit of magic. There's a bit of these things are actually related to things. I don't want to go through the derivation, but they can be related. So if you have a fluid that you want to simulate for which you know the shear viscosity mu or psi, the bulk viscosity, then you can, for that scheme, you can derive what this alpha and theta should be, and then you can actually do the simulation correctly. And so I showed at the start the simulation of, trying to show the simulation of these boats. Now just using order, it should be Navier-Stokes equation. These coefficients are well known, so you can then, they can be measured, so you can then apply this kind of conditions and actually have the fluid now behave like water and not like an ideal gas. We also have to change the equation of state. Now the thing is, then that's where it becomes a bit tricky and a bit of a dark art, and that's where different people doing SPH will do different things. Is that this shock treatment, I didn't specify just being applied everywhere, because I just added to the equation terms, but that's not necessarily what we want. We don't have shocks everywhere in the universe or in this room, only at specific points where there are specific conditions of motion and so on that are being applied. And so what people do is that we have to detect somehow, based on the property of the fluid, saying, here it looks like a shock is taking place. I'm going to activate that extra term. And then later on say, oh, now I'm far away from a shock region. I should deactivate that extra term. And here, there is no good way, or there are many good ways, but no excellent way. It's more like different people have different implementation, will use different ways of detecting things, and will argue that for their specific science case, their way is the best compared to something else. So depending on the type of problem you want to solve, you may have different options here that people will use. So, yes?
I'm thinking to measure the pressure gradient in particles, like it's not a universal supply, basically a universal solution.
So you want to measure the gradient of
The pressure gradient between particles,
yes,
and where it's happening to show.
Correct. So that would be one of the first things you do is measure the difference in pressure between the particles. Say, oh, if it's very large, surely some shock is happening.
Why is not a universal solution?
So it is a good idea, and it is part of this. Now I can give you a counterexample. So if I now have let me take a potential well. Right? I have a halo, and I have a gas in equilibrium in that halo. So the gas has a temperature that makes it fight against gravity. Do you see the concept? Right. So then the pressure in that potential well is different at different radius, because the amount of, if you are in the center of the potential well, there's more gravity, more potential energy you have to fight against than if you're outside. So there's a gradient of pressure. Right. This radius. But now that gradient of pressure is not generated by a shock, it's generated by gravity. So if I use your scheme and say, whenever there is a gradient of pressure, I have to do a correction for shocks, I'm doing a correction for shock here at the wrong place. So your condition is good, but it's not good enough. So you have to actually use multiple tricks and decision making about what is happening to only apply where you want. But you're right, the gradient of pressure is one of the key parts. So then what people do, and we're going to be running one of these this afternoon just to get started. There are some very standard tests. Yesterday we talked about gravity. Gravity is hard because there are very, very, very few problems where we know the solution. And apart from like planet things, but anything that's more complicated, like collapsing objects, we don't have a solution with pen and paper and we can drive and test whether our code is the correct answer. In fluid dynamics, there are many problems where we know the solution, and then we can test whether our code gives the correct answer. So the classic one, for instance, here is taking a tube, like a very one-dimensional, you can even do it in the lab to verify that this is how it works. You can take a very long tube, then you have a given density, pressure, velocity on one side, density, pressure, velocity on the other side, and then you open, then you have a mini wall in the middle, you remove that wall, and these two phases interact. And it's called the shock tube because it will usually generate a shock and many other features, and then this can be calculated analytically. So for instance, here you have, in the red line is the true solution. If you go pen and paper, you derive the whole thing, and then the code will do something like the black holes. Okay? So you can see that in some regions it's not doing great. Here is a huge jump. This specific version of the code here, clearly it's not doing so, it's doing something funky here, right? There's something that is not quite right. There is a spike, and then it goes down. And then here, that should be completely flat, but somehow something is going on. And so, what I mentioned before, you have these different switches where you say, oh, but here, actually here there's a jump. So maybe I should be treating that jump, so I need to have a correct switch to decide when this jump is going on, I should do this correction, and so on. And so there's a lot of debates in the literature and people fighting over what is the correct way of fixing all of these specific features. Some of them we don't care about because they don't matter, and some of them we do care about because they have impact on actual physics problem we care about. So this afternoon we're going to be running that problem just to get us started with then we do something more fun, but we're going to get running that tube. So you can see, for instance, that specific version, we don't have that problem here, but it's because it has some different combination of these dark art decision-making algorithms. It still has a very spiky business thing going on here, but that's solvable this other way. So we're going to be running this just to get us started with running fluid dynamics. And then here's another problem that people like to show. I think I've already shown you at the very start by the moving grid thing, but this is another, it's called the Kelvin-Helmholtz instability problem. It's quite interesting. So what you do here is that you have one fluid going this way in the middle layer, and then you have two fluids going the other way around, and they have the same pressure, and then hopefully that should now work on the cable. Right, so you have the red fluid, I think, is going this way. It's the same fluid, right? It's just colored for convenience. The red is going this way, the blue is going the other way. They're just passing by each other. And then that will create some sort of turbulence at the interface that's going to be creating this rotational pattern. It's called Kelvin-Helmholtz instability. And so then ultimately these two layers will mix and we'll get some sort of smooth interface in between. So that problem, we don't know what the exact solution of that problem is, but people like to do in simulation because it actually looks quite nice. You know, this rotating vortex and so on. Now you can say, well, why do we care? Okay, it looks nice, but is it an interesting problem to ever study? Well, here's an example. Bunch of mountains. You have a bit of static air, and you have another layer of air passing above. So very similar setup. If you only think about the top half of my movie, and the clouds sort of trace exactly where these vortices are taking place. So it's something that happens in nature. Now, if you think Earth stuff is boring, I want the space stuff. Here's another example. You know what this one is? Yeah, it's the big red dots on Jupiter. But if you look in more details, you can see all kinds of vortices, rotation things that have exactly the same pattern, because you also have, for Jupiter is not just a uniform sphere, you have different layers rotating at different speeds and so on. And I don't know more of the details, I definitely don't work on planets. But all of these different layers working at different speeds exactly gives this sort of interface where you have a bit of shear between the layers, and all kinds of vortices can be seen on all kinds of sizes, and even the big red storm could be thought of as being one of these vortices. So that actually happens, and I think this is another example we can play around this afternoon. Any questions? Before?
How do you know how to tell to the code which one is the perfect smooth delay?
Yeah, so that's the one and only free parameter you have, right? As a user, you have to decide how many neighbors we want when we sort of adjust the size of the neighborhood.
For example, in the initial conditions,
Yeah.
if you generate 2,000 particles with a uniform distribution, you
Yeah.
can tell which one is like closer.
Well, so if you have a using distribution, so what the code will do is the code will have to search for the neighbors around each of the particles. So in the initial conditions, we don't have to specify an age at all, because that is set during the calculation. So what you as a user have to decide is how many neighbors, how many particles you want to use when you search around you. So then you can think of, if you have too few neighbors, if you only have 3 or 4, then that means every value you calculate is going to be very imprecise. There's a lot of noise because you only have 4 neighbors to calculate this sum. If you have 10 million neighbors, then it means you're looking for very, very far away, so you're smoothing all of the information over very, very large distances. So you want not too few and not too many. Typically, people like to use around 50 neighbors or something, because then it means the noise level is small. Right? You can think of the error you use to be like the Poisson statistic, so maybe like a couple of % of error on the measurement. And it's not too many, because if you wanted to make more precise, then the code becomes more and more expensive. So that's the one number that you as a user have to choose how precise you want this to be. Typically, people don't change it. They say, oh, 50 is good. And then they just run it. Because they tested that it makes very little difference. If you do 48 or 60, they're basically the same answer. So it's good enough as a guess. Okay, so just to tell you what we're going to do this afternoon. So we're going to again run the same piece of code, but now instead of running gravity, we're going to be running some aerodynamic things. So just to get us started, so we can see how everything works, what we're going to do is just run one of these standard tests, either the Gary Hamels, the vortices, or one of these. There are a few examples. So if you downloaded the code, you have already downloaded the code comes with a lot of examples. Some of them we can just run and make movies and see whether they look like Jupiter or clouds or something. And then the other one, which is a bit more experimental, is going to be a bit more on you to do some coding. What I would like to do is that we're going to take an image, right, and we're going to turn anything, and we're going to turn that image into a density field. And then we're going to say this is the start of my simulation. We're going to let that image evolve into whatever fluid dynamics equation tells you. So that's not physics, but it's more about learning about how these codes work and how something just works. It's a bit more fun, and it's actually quite quick to run. There is an example that I did last night. So first question, so one thing that works quite well is to take square images. So I do some album cover. There's bone spots, if you know which band. Pretty good, Bigfoot animals. So I turned the cover here into a density field. So I think yellow is high density, blue is low density. And I just then run my simulation. And it just dissolves and it creates ripples and waves all around. And so that's just running the code with some setup. So the goal for today would be take an image, generate. Right, now we have to generate the particles that have the correct density to represent the image. Press play and it goes. The more fun is to run the movie backwards. Good, yes?
It dissolves just like the band.
It dissolves just like the band, yes. Good. Any question on anything? If not, then I'll see you this afternoon.